good evening, everyone, or good morning, depending on where you are today. So I'm going to talk about machine learning at the wireless edge. And this combines sort of two areas of very rapid technology development, wireless communications and machine learning. And both of these areas of technology are not new, they're old. Decades old in both cases, but both have taken considerable advancement in recent years. Wireless because of the rollout of new generations, particularly 5G, starting to think about 6G, and machine learning because of the availability of large data sets and powerful computing. So I'm going to talk about the convergence of those. I'm going to talk in particular about one aspect of that, and let me describe that in the next slide. Here we go. So when talking about machine learning and wireless communication, there are really two things to think about. One is using machine learning to optimize wireless networks. And that's a very rich area, and there's quite a bit to do there. I mean, a lot of what's done in communication networks is decision-making or optimization. Of course, these are the things that machine learning is good for. So there's a lot of natural applications of machine learning in the optimization of wireless networks. And this is becoming increasingly important as networks become more complex. On the other side is using mobile networks as platforms for machine learning. And that's what I'm going to talk about today. And before I go on, let me just mention this book that's shown below here. That's in press now, Machine Learning and Wireless Communications, where there's a lot of detail on both of these aspects of machine learning and wireless communication. So I think it's currently in production, so hopefully it'll be out sometime this summer. So let me say what I'm going to talk about today. I'm going to talk, first of all, I'll motivate a bit the problem. Then I'll talk about two types of edge learning, federated learning and decentralized learning. And I'll describe what I mean by those soon. And then I'll wrap up with some conclusions in which I'll also talk about some open problems. By way of motivation, let me just say that, of course, say a little bit, of course, this is way oversimplified, talking about the state of the art in machine learning. So as I mentioned at the beginning, there's tremendous progress in machine learning in recent years. It's not a new topic, and many of the techniques are not new. They're improvements on existing techniques. But what's happened is there's more and more data available, partly because of mobile networks. And then there's been a significant increase in computational power. So these two things have converged to make machine learning more practical and more powerful, and expand the number of applications that it can help with. I would say, again, grossly oversimplifying, there's a standard kind of machine learning, which is implemented in a centralized manner, that is in a data center or cloud, where the machine learning algorithms have full access to data and can manipulate all the data centrally at one time. And some of the state-of-the-art models are, for example, deep neural networks that can run in the cloud. And these are managed and operated by some standard tools like TensorFlow, and they can be accelerated by specialized hardware like GPUs and TPUs. Okay, so this is, again, a very broad brush look at the state of the art in machine learning. Now, at the wireless edge, there are some issues that make centralized machine learning like this unsuitable for some applications, such as self-driving cars, first responder networks, healthcare networks, and so forth. And why are these applications different? Well, first of all, for one thing, in these kind of applications, data is really born at the edge. It comes through iPhones, cell phones, or IoT devices. Often the capacity for backhauling data is limited. Low latency is at a premium in these kind of applications, and high reliability, of course. Data privacy and security are also paramount in many of these applications. and you are interested in being able to scale the applications very broadly, but they usually have some locality associated with them. That is, the things you're trying to learn about are really location specific. So it's not necessary really to aggregate data from multiple locations. So these considerations motivate moving learning closer to the network edge. So I'm going to talk about, so there are three ways to think about machine learning, at least in the context of my talk today. One is what I just talked about, standard machine learning, where data is collected at the edge, say, of a network. It's backhauled to the cloud, learning goes on there, and models are distributed out to the edge again from the cloud. Another is federated learning, where data remains with end user devices. End user devices have enough power to do learning on board, and then models are shared with something like an aggregator, say an access point or a cell site, a base station, where models are aggregated and then redistributed out to the edge. Okay, so this is federated learning, and typically there are multiple rounds of that kind of sharing of models and aggregating and updating. And then another is decentralized machine learning, where there is no aggregator and all communication is peer-to-peer. And so the end user devices are collecting data, building models, and in some way communicating in a peer-to-peer fashion in order to optimize their models. And so I'm going to talk about the latter two in succession. So let's talk about federated learning. So what's the basic architecture of federated learning? Well, the idea is to enable end user devices to do machine learning without centralizing data. And some key features, which I mentioned already, one is end users keep raw data locally. They don't backhaul data anywhere. It remains on the end user devices. There's training on device, and in federated learning, the end user devices are training a shared model. So in the end, they'd all like to have the same model. And then there's federated computation or aggregation. So an edge node, like an access point, collects trained weights, or this could be gradient updates, but I will talk about trained weights in this talk, from end users, and then updates the shared model. Then that shared model, the updated shared model, is redistributed to the end user devices, and they can update the model again. The process is then iterated until convergence. Okay, so that's the basics of federated learning. Now, if mobile networks are wireless networks, of course, so there's some issues to think about with federated learning. Federated learning, by the way, is not necessarily a wireless technique. It was originated as a means for distributed machine learning, but it's tailor-made, you would say, for wireless networks. Some issues that need to be addressed in using machine learning in mobile networks are the following. So first of all, the communication to the access point of the models needs to go through wireless channels. So the wireless medium, of course, is a shared medium, and it's resource constrained. So these cause some issues in the design and analysis and performance of federated learning. So one issue is that only a limited number of devices can be selected to update their models in each update round. That is, to upload their models in each update round. And secondly, even if a device, an end user device, is selected to update or upload its model, the transmissions aren't reliable necessarily because of interference, okay, or other impairments in the wireless channel. So there's a couple of questions that we need to address in applying federated learning in mobile networks. One is, how should we schedule devices to update the trained weights? And secondly, how does interference affect training? And I'm going to talk briefly about these two things now. All right, so scheduling. So what kind of scheduling mechanisms can we use? Well, there's some standard scheduling mechanisms that we can consider, and I'm going to talk about three of them now. One is random scheduling, where we have K end user devices, And there are N channels that can be used at any one time for uploading data. N is less than K, otherwise there's no scheduling problem. So the access point is going to uniformly, for random scheduling, the access point will uniformly select N out of the K end user devices at random. Okay, that's one scheduling mechanism. Another is round robin. So in round robin, the access point groups end user devices into groups, and they're going to be K over N of those, and then sequentially selects the groups in a round robin fashion for updating. So it's a standard technique. Proportional fair is another scheduling mechanism we can consider. There, the access point looks at the quality of the signals from the various end user devices and selects N out of the K that have the strongest channels, basically, the strongest signal to noise ratios. And this is relative to their historical SNR. So we can look at the performance of these three scheduling mechanisms to see if there's any difference in how federated learning performs based on scheduling, choice of scheduling mechanism. So there are a couple of things we have to consider. One is, first of all, the training update. A training update can be successfully received by the access point from an end user device if and only if two things happen. One is the device has to be selected for upload. That's the scheduling mechanism. And the other is the signal has to be correctly decoded from that end user device has to be correctly decoded at the access point. So one way to model that consideration requirement is that the received signal to interference plus noise ratio at the access point or aggregator has to exceed a decoding threshold. And here's a formula for the SINR. And the main thing to think about here is the threshold theta, which is a parameter of the system, of the physical layer system. Okay. So one way we can compare different scheduling mechanisms in this situation is to look at the number of communication rounds required to reach for the federated learning iterations to reach a certain accuracy. And in what I'm going to talk about now, the machine learning problem that we're going to look at is the optimization of a minimization of a strongly convex cost function, in which case the primal and dual problems have the same solution at the solution. And an epsilon accurate solution is one where there's a difference between primal and dual solutions is epsilon. So epsilon is just a measure of accuracy that we can throw out. So there's two parameters here: theta, which is the decoding threshold. It's a measure of the quality of the channel, the physical channel, and epsilon, which is a measure of the quality of the solution that we're looking for. And with these two parameters and a few others, which I'll describe here, we can actually get lower bounds on the number of communications rounds for these three types of policies: random scheduling, round robin, and proportional fair, to achieve an epsilon accurate solution. And the parameters of that are epsilon, the accuracy, N, which is the total number of exemplars out there in the system, alpha, which is a path loss exponent. This is a wireless channel, so it has a path loss exponent. Beta, which is an abstraction of how precise the learning is at the end users. And then theta, which is the parameter that measures the quality of the communication link. And then there's this nu here appearing here, which is, remember, G is the ratio of the number of channels to the number of end user devices. And nu is just an integral function that depends only on the two parameters, theta and alpha. I haven't written it here. So here we have lower bounds. We don't have expressions for these. We do have lower bounds, but I see something in chat. Let me be sure this is okay. It's not for me. Okay. So these are lower bounds, and they're really not very meaningful in this form. There's just some mathematical expressions. So let me just show you an example to give you a sense of what's going on here. Okay, so this is an example where each access point has 100 end user devices to consider with 20 subchannels. What I'm showing here is that a normalized version of that lower bound for random scheduling, round robin, and proportionally fair scheduling for two different for two different access for different link qualities. So when theta is high, that really means that the coding is weak. So that's a weak channel. And when theta is low, that means the coding is strong, and that's a strong channel. So on the left, we have a strong link. And you can see that random scheduling and round robin perform roughly the same, whereas proportional fair is much better. On the right, where we have a stronger link, you can see that random scheduling and proportional fair perform worse than round robin. And these are intuitively reasonable results, because when the link is weak, you need to be sure that the signal to noise ratio is high, and proportional fair does that. Whereas when the channel is strong, or when the link is strong, I should say, round robin just gives everybody an equal chance to upload, and that's better here in that case. Now, these are lower bounds. So what does that mean in a real machine learning example? Well, here's an example where we look at the MNIST data set. So the MNIST data set is a set of handwritten numeral recognition. It's a handwritten numeral recognition problem with a lot of exemplars marked. Okay, that's the MNIST data set. And here this is just an example where we choose to optimize a support vector machine on that data set using federated learning. Here we have 10,000 sample points distributed evenly on 100 devices, and 20 can be selected for each round of aggregation. So K is 20, N is 100, little n is 10,000. Okay, and on the left it shows the loss, and on the right it shows accuracy. And here we just compare random with round robin, because that tells us about the proportional. This is a case where theta is low. So this is a case where round robin is shown to be better, at least by the lower bound, and random and proportional fair are roughly the same. And that's borne out here. You see that on the left, where we look at loss. Loss is a lower loss is achieved more quickly using round robin. And on the right, we see accuracy, which is percent correct. And we see that greater accuracy is achieved more quickly with round robin than with random scheduling. So this bears out on a real example, the lower bound, what we observed with the lower bound. I didn't put it here, but theta is small in this case. So one question is, can we optimize scheduling? So we see that scheduling matters. Question is there an optimal way of scheduling? We just compared 3 standard scheduling mechanisms, and we did see some differences, but is there a way to optimize? And one way to optimize is to look at a design metric called age of information. And many of you may be familiar with this. Age of information is a design metric that's arisen in applications like sensing and IoT type networks, where we're not only interested in the traditional metric of fidelity in measuring the performance of communications, but we also are worried about the freshness of information. And so you might think, for example, about looking at the daily temperature. You're much more interested in knowing today's temperature with low accuracy than you are in knowing yesterday's temperature with very high accuracy. So the age of information matters in addition to the quality or the fidelity of the information. So AOI makes a lot of sense too in looking at federated learning. So although it wasn't developed for this, it's a good metric to look at for federated learning. And in this context, we can define the age of information at each end user device. Say the ith one is how long it's been since it was chosen for update. So during each round, if selected, the age of information for a given device drops to 0. Otherwise, it increments by 1. So for device I at time t plus 1, little t plus 1, the age, capital T, either increments by 1 or goes to 0, depending on an indicator of whether the device was selected or not. So SI of T is 1 if the device is selected, and it's 0 otherwise. So we can actually use the age, and I don't have the details here. I should mention here, there's a paper here, an ICAS paper from last year, where we look at this in a little more depth. It turns out a polynomial time algorithm for minimizing average age. And so it's possible to do that between iterations. And when we do that, we can, again, see a difference between doing that and a more conventional type of scheduling. So this, again, we're looking at sport vector machine on the MNIST data set, same example as before, excuse me. And we're comparing the wireless round robin, which is the one I just described, that is the one that minimizes the average age, with something called maximum pack, which just simply tries to pack in the maximum number of uploads on each round. And you can see that we can optimize, at least between these two, and certainly intuitively in general, by minimizing the average age of information in the update rounds. So I'm going to move along because I want to get to some other things too. But let me talk a little bit about privacy, and I think this fits in with the theme of the Cryptic Commons well. So one of the early claims about federated learning was that it was privacy preserving. And the reason for that is because the data always remains with the end user devices. So the data is never shared with anyone. So the original claims by some important organizations and some smart people, and even some not so smart people like myself, was that it was privacy preserving for that reason. And then subsequent studies have shown, however, that this is not the case. And intuitively, it makes sense that it's not privacy preserving because the parameters of the model or the gradient updates that are shared by the end user devices are functions of the data. Therefore, there's clearly some mutual information between the shared information, that is the parameters or the gradients shared in the updates, and the original data. And in fact, you can make some pretty strong inferences in certain cases about the end user data from those updates, the shared updates. So it's not really privacy preserving. And that becomes a concern in a lot of applications. I mean, for example, healthcare applications, any application where you're worried about sharing private data. And so there's been a lot of interest in recent times at trying to make federated learning impart some degree of privacy on federated learning. And one approach, which I'll mention briefly here, is to use differential privacy to protect end user data in federated learning. So let me just say a little bit about that. So I think differential privacy may be well known to this audience, but I'll just say a word about it. So generally speaking, differential privacy refers to a type of privacy in which two data sets, one having private information and one without it, but are otherwise identical, can't be distinguished by statistical query. And we have to say with high probability here because it's not an absolute. Okay, so this is a very powerful, it's been a very powerful technique. Differential privacy is used widely now. There's some issues with it, but it is widely used in protecting privacy of databases. Okay, so one way of achieving differential privacy is to add noise to data. Okay, and you can show, depending on the level of the noise, you can show the degree to which privacy can be maintained. And this approach can be used in federated learning. But what happens is you create a trade-off between privacy and performance when you do this, because adding noise to the data, of course, diminishes the quality of the model. The data here is I should say you're adding noise to the model, the parameters that are being shared with the aggregator. Okay, so naturally that is going to cause problems with the performance. Okay, so there's going to be a trade-off between privacy and performance. The more noise you add, the higher the privacy, but the poorer the performance. And I'll just show you a simple example. This is from a paper that appeared in the IEEE Transactions on Information Forensics and Security last year, late last year. This shows just an example. Again, this is now using a convolutional neural network on the MNIST data set, 10,000 sample points on 50 devices in this case. And what we're showing is testing accuracy versus, so the percent correct, versus aggregation time. You can see that, and the parameter epsilon is a privacy parameter. So epsilon is infinite when there's no privacy, so you don't apply differential privacy. And the smaller epsilon is, the higher the degree of privacy. So epsilon is basically appears in the exponent of a number that appears in a bound, and the larger it is, the looser the bound. Okay, I'm leaving out a lot of detail, but it's in that paper if you're interested. And you can see that there's a clear trade-off. If you think of epsilon as the measure of privacy and test accuracy as a measure of performance, you can see there's a clear trade-off between privacy and performance. There's also, and I'm not showing it here, but if you look in that paper, there are also trade-offs between privacy and convergence rate. There are also trade-offs if you have, the more aggregators you allow, the more devices you allow to aggregate at a time, the greater performance is for a given privacy level and so forth. So there are a lot of trade-offs there. I just wanted to give a simple example, but I encourage you to go look at this paper if you're interested in more detail. I do want to spend a little bit of time. I see I have I'd like to spend maybe about 15 more minutes and then take questions if there are any. I want to spend a little bit of time talking about decentralized learning. So we talked about federated learning, where we have an aggregator. And now I want to talk about decentralized learning, where we only have end user devices. So we only have the edge, and all the communication is peer-to-peer. So you might think about an IoT type situation with very light infrastructure, where a lot of the communication goes on peer-to-peer, or other sensing or applications of that sort. So in thinking about this kind of model, this kind of situation, we can first step back and think about a general model for distributed learning. So learning is based on, at least supervised learning is based on exemplars. That is, you have examples, you're typically trying to learn, you have inputs and outputs of a function, and you're typically trying to learn the function. So if X's are the inputs and Y's are the outputs, a pair of marked inputs paired with correct outputs is an exemplar. Okay, so if we have a training database of, say, n exemplars, it can be used by M learning agents. Okay, these could be smart sensors, these could be cell phones, this could be whatever. And then you can think about a bipartite graph model for learning, where the learning agents are connected to the training database through edges of the bipartite graph. And so for here, so learning agent 1, it can see exemplar 1, exemplar 3, and some other unnamed exemplar there. Learning agent 2 has another subset that it can see, and so forth. Now, this model is general. It could include, for example, centralized learning. If you just have one learning agent and it's connected to every training datum, then that's a centralized learning case. You could also put federated learning in this context, but you can also put decentralized learning in this context, fully decentralized learning, where you have M learning agents and M equals N. So the number of learning agents equals the number of training data points, and the connect. So they're basically, each learning agent has its own exemplar, its own data, and then there's connectivity depending on the topology of the network. So I'll be a little more specific in a minute. So think about this general model. And a natural way to do learning in this general model is local learning. That is, each learning agent could learn from the exemplars that it has and fit the model that it's looking to fit. So that's very natural. It preserves the locality of the data and the connectivity that's described by the bipartite graph. But a problem with local learning is that it's locally incoherent in general. So that is, for example, in this example, learning agent 1, so if f is the function that they're trying to learn, so f of x equal y, they're trying to learn f. So learning agent 1 is going to have its own estimate of f, f1 hat, and learning agent m, say, is going to have its own estimate of f, fm hat, based on the data that they see. So they have different data, but they share one data point here, the first one. And local incoherence means that if they each learn their model separately and then apply it to the same data point, they're going to get different answers. Okay, and that's going to happen in general unless they share exactly the same data points. Okay, so you can prove that local incoherence is non-optimal. That is, there's going to be a better scheme based on this particular graph of learning that's going to give you a better performance, meaning a lower mean squared error in this case, and it's not locally incoherent. And here's a way to achieve that. Okay, so this comes from an old paper, actually, from 2009 with Joel Pred, one of my former students, and Sanj Kulkarni, one of my colleagues. And here we looked at this model and looked at a general type of collaborative algorithm in this model. So here's a simple example with 4 learning agents and 7 exemplars. And the way this algorithm works is, first of all, learning agent, we go in sequence for the learning agent. So we start with learning agent 1. It learns from its exemplars. And then from the exemplars that it's connected to. And then before passing things off to the second learning agent, it overwrites the targets, that is the Y's, in its exemplars with its own estimates of those Y's. So it sends information about its learned model down back into the database. And then we move on to learning agent 2, and it does the same thing with the learning from its examples, some of which may have been modified by learning agent 1, and so forth. And we iterate around until we get convergence. And then it turns out that you can use alternating projections to show that algorithm converges to a coherent relaxation of the global solution, and a relaxation of the global least squares in this case to the structure imposed by this bipartite graph. Okay, so it's basically optimal. It converges to an optimal fit within this constraints of this graph. Okay, so here we can look at an example to illustrate that. So here we'll look at a simple case where we have 50 sensors uniformly distributed in space on a line between -1 and 1, uniformly random, I should say. And then each sensor is observing some function f of its location plus noise. And the noise here we'll just assume is white Gaussian with unit variance. And the regression function f is linear. And then we'll define so that sets up the model. And then we'll define the topology, that is the graph, the bipartite graph, to say that 2 sensors are neighbors, that is, they can communicate with one another if they're less than r apart, where r is just a parameter of the model. And then they're going to do, this is kernel learning we'll do here, and they're going to use a linear kernel. So this is an easy problem. We have a linear regression function, we're doing kernel learning, but I just want to illustrate the distinction between local learning and this collaborative algorithm. And so what's shown on the right here is the test error, which is mean squared error, versus connectivity, which is measured by the size of the neighborhood R. So if R is big enough, it's all fully connected and you have centralized learning. But the smaller R is, the less connected it is and the more distributed things are. So the solid line, which you can hardly see down at the bottom, is the fitting of centralized learning. And that's very good because it's a linear kernel and it's a linear regression function. And then the dotted line at the top is the performance of local learning. You can see that R has to be pretty big. There has to be a lot of connectivity before local learning becomes as good as centralized learning. R is 0.6 out there at the right, if you can't see it. And then the dashed dotted line, which is down closer to the bottom, is the performance of this, it's called SN train here. It's the performance of this collaborative algorithm. And you can see that with a relatively small neighborhood size, 0.2, it's already achieved centralized learning, the performance of centralized learning. So this just shows that by collaborating, these sensors can attain very good performance that can't be obtained just by simple local learning. I want to speak, so that's a system where we're trying to fit a function by minimizing mean squared error. I just want to mention briefly also another type of learning, which is reinforcement learning, and talk a little bit about decentralized reinforcement learning, and then I'll wrap up. So reinforcement learning, of course, is a way of finding a decision or optimal decision or control strategies without a model. Okay, it's applied to Markov decision processes. Okay, and Q learning is a type of reinforcement learning where you update a so-called Q function, which is the payoff iteratively, trying to converge to an optimum. Okay, and typically you do that using gradient descent when you have full data. Now, if you have a distributed setting, you don't have all the data, you only have connectivity like was shown before. So the Q function can only be updated based on what each individual agent knows, plus what it can get from its neighboring agents. Okay, so if you use classical gradient update, doesn't work very well in that situation. But if you combine a classical gradient update, a local one, with a consensus update, consensus among neighbors update, it turns out that you can get convergence to global values, okay, if you use the right tuning constants and so forth, and you have some connectivity conditions on the graph. Okay, so this is also a somewhat old paper. This is with Jose Moura, Carnegie Mellon, I'm sure you know him, and Shomo Card, another former postdoc in my group. It appeared in the Transactions on Signal Processing a number of years ago. And I'll just show you an example. Here's a very simple example where we have binary states and binary actions. So there's the Q function has 4 values. We assume there are 40 agents. And then we define that bipartite graph by looking at 2 nearest neighbor connectivity. And on the left, we show the convergence to centralized. So the dotted, we picked out a typical agent. So there are 4 values. The dotted line is the convergence of centralized Q learning. And the solid line is the convergence of, for one particular agent, of this distributed algorithm, fully distributed or decentralized. And you can see that they do in fact converge together. On the right, this just looks at the convergence to consensus. So this picks out 10 agents of the 40, just 10 at random, and shows their Q functions converging to consensus. That is, it shows that they're all going to achieve the same result. Okay, so the theory tells us this, but this just shows through example that it's true. So let me wrap up now and see if there's time for questions. Leave time for questions in case there are any. So first of all, the basic conclusion here is that wireless networks can be platforms for machine learning. I talked about federated learning, where edge devices like access points interact with end user devices to learn common models. I talked about decentralized learning, where end user devices interact with one another to collaboratively learn models or actions in the case of reinforcement learning. And I want to mention a few issues for research. First of all, there are a lot of things to think about here. This is what I've shown has been a very pristine models for what's going on and what would be going on in the real world. One is model efficiency. So if you're thinking about doing learning on end user devices, the resources are going to be limited. So the energy available, storage, computational power, all that's going to be limited. So there are going to be trade-offs between, if you use a neural network, for example, to do the modeling, number of layers, number of neurons per layer, and so forth, and other qualities of service and performance. So there's a lot of interest in this, and there's a lot of work ongoing. But before you can do this in end user devices, you need to worry about all these practical matters. Another issue is communication efficiency. So in what I've looked at here, I haven't done any coding across devices for uploading, for example, in federated learning. So because all of the end user devices are trying to learn the same model, there is some correlation among them. So this is a classic distributed source coding problem where you have correlated sources that you're trying to encode. So it's a Wiener-Ziv problem. So that should give some additional efficiency in federated learning, and there's some ongoing work along those lines too. Another one is that this is when we're talking about learning at the edge, we're not talking about big data. So a lot of machine learning is developed for large data sets, but usually you're going to have sparse data at the edge. So the training sets are going to be small. So to make it learning more powerful, you can incorporate domain knowledge or some knowledge of the physics. Okay, and there's a lot of things like deep unfolding and so forth that take advantage of models to do model-based machine learning. So-called gray box machine learning, which is really important here for this kind of application where we don't have much data, and we may also have good physical models. And then finally, security and privacy are issues. I already talked about privacy, information leakage through gradients or model parameters, but also another issue is security, because once you have distributed agents doing things, you can have malicious devices. So malicious end user devices can try to interrupt the performance. They can provide adversarial training examples. They can send, they can try to poison the aggregator and aggregations and so forth. So again, there's a lot of interest in those issues as well. But there's still a lot to be done in all of these areas. I'll just mention some recent papers of interest. I mentioned this paper by Wei on differential privacy. There's another paper which appeared in IEEE Network last year, which also looks at a number of issues in privacy and security. It's a review paper. Some issues on communication efficiency and coding, papers from this year, one in JSAC on fast convergent federated learning, one looking at compressive sensing to try to look at the sparseness and so forth, one looking at quantization, and a general review paper from PNAS, that's the Proceedings of the National Academy of Sciences, on communication efficient federated learning. So I think I'll be happy to share these slides, so you don't need to worry about writing this stuff down. So, and with that, I'll say talk and be happy to take any questions.
Thank you very much, Professor Poor, for a very interesting keynote. I see that we already have a couple of questions, but before that, I would like to encourage you all to just turn up your mic and give a hand.
Yay!
Thank you.
Thank you.
Thank you.
All right, I think the first question is from you, Adrian. I would like to, would you please like to pose it yourself?
Yeah, that's great. Thank you, Jonas. Thank you, Professor Poor. That was a wonderful talk and just really so helpful to an outsider as an anthropologist. I could I could follow along with a lot of it. So that was really great. Thank you so much. I think you probably answered part of the question after I wrote the question in the chat. But I'll ask it anyway, and maybe with a more specific focus. So what I asked was, what are the drawbacks of decentralized learning? And you did mention some of those things, but I think my question is really about what we're calling actual world implementations. So what kinds of examples are there for actual world implementations of decentralized learning and this computing on the edge? And in those specific cases, what are the drawbacks to them in terms of privacy and security, for example?
Yeah, so that's a great question, Adrienne. Thank you very much. So one of the examples that is often discussed is automated driving, because the cars have a lot of sensors on them, and of course they have a lot of sensitive data, like where they are is a bit sensitive, for example. But there are multiple reasons for doing federated learning there. One is that they have so much data. A lot of it is image data, and there's radar data and so forth. They're collecting about their environment that sharing all that data is already an issue. But also there's privacy issues and security issues connected with that as well. But you might think about multiple cars are driving autonomously in a certain area, and they all need to know certain things about the area, like what are the traffic conditions, maybe what are the weather conditions and things of that sort. And so they're trying to learn a model for something about their environment that they're driving in. And so they each are collecting data. They each have a lot of sensors on them, and somewhere there's an aggregator that's going to try to help them use each other's data in the way that federated learning shows. Naturally, there's a lot of concerns with security, because if a malicious actor could try to confuse the autonomous driving system so that it swerves off the road or stops in the middle of the highway or something like that. So I mean, those kind of issues are paramount. Safety is probably the most important thing in autonomous driving. So those kind of issues are paramount. Another area where federated learning has been discussed, and this is not necessarily wireless, but it could be, is in healthcare. So forget about the wireless aspect and just think about the situation where you have multiple medical facilities that are collecting data on patients for having the same disease or the same symptoms, and they would like to share that data. They'd like to build models for predictive, trying to predict, say, diagnose from the symptoms or some other thing, predict the quality of treatments and what have you. But they don't want to share the patient data. In fact, they're not allowed to in the United States, and I'm sure the same in Denmark. They're not allowed to share the private data of individual patients. So they'd like to build a model based on the patients they have, but they'd like to have a stronger model, which they can get by also using data from other hospitals and so forth. So that's another example that's often discussed for federated learning. It could be mobile, so it could be wireless, but that aspect of it doesn't necessarily come into play there. But there are obvious privacy issues there. I mean, you can't really share private information just by law. So the issue of privacy is a big one there. So those are two examples that are often discussed for federated learning, and I think they both are ones where privacy and security are pretty important. I hope that answers your question.
That's fine. That's great for now. Thanks.
Thank you very much. I think we have approximately 5 minutes left before the break. So I think we should move on to your question, Rafael.
Thank you very much for this very interesting talk. I have more technical questions, and actually it's kind of reveals, even though I'm a technical person, I want to ask something which I didn't understand, and Adrienne is saying that she understood everything, so I feel really ashamed of myself. But here you go. The question is about how much linearity plays a role in the federated learning. It sounds like the construction is very much leaning upon there is some kind of linear operator one works with. Is it a right impression I got?
Yeah, actually, I may have given a false impression there. The example I gave at the end was one for linear regression, but generally it's not linear. I mean, the models are usually neural networks, which are, of course, highly nonlinear. So that is typically is not linear, actually. So I think I gave you that one example, but you know, some of the other examples I gave you support vector machines, which are not linear necessarily, and other examples using neural networks and so forth. So there's no real presumption of linearity there. Sometimes, by the way, in analysis, people will assume linearity to try to get some better understanding, but that's not really in the typical application. I don't think you would really expect to see linear regression. And
also very quick question. I know we don't have so much, but it's tricked me a bit with reinforcement learning. So yeah, I presume it's still it is distributed reinforcement learning is still convergent. And what are the assumptions? Are the assumptions for convergence exactly the same as for ordinary reinforcement learning? For example, rate of forgetting factor, or are they, in other words, are they the same, or you needed to impose some extra conditions?
There are two extra conditions. One is connectivity. Well, of course, it's not an extra condition, it's a relaxation of a condition. I guess in regular reinforcement learning, you could think about having a decentralized setting where everything is connected to everything else, fully connected, right?
That's right.
In decentralized, you need to have the assumption of connectivity of the following type. That is, I think it's, if you look at the graph Laplacian, the technical thing is the second eigenvalue is non-zero, which means that you can get from any one point to any other point through multiple hops. Okay, so it has to be connected in that sense. And secondly, there are tuning constants, just like there are in any iterative algorithm, and they have to go to zero, but not too fast. And there are two sets of them, one for gradient updates and one for consensus updates. And there are some technical conditions on how those tuning constants have to go to zero. But so it's similar types of things, but there are additional features there.
Yes, yes. Thanks a lot.
Sure. Thanks for the question.
All right, we have one more question in the chat, and I think we should move on to you, Kyung-Soo. Please.
All right. Thanks for the talk. It's quite interesting, and I have actually a few questions. First one is like, except I know that in the field of privacy preserving, lots of people are using this notation of differential privacy for guaranteeing privacy. But in federal learning, other than differential privacy, for example, how about secure multi-party computation? Are they widely used in federal learning? How do you think of the pros and cons of compare with differential privacy technique?
Yeah, there are other methods, and a lot of them do come from things like multi-party computation. So as far as comparison, I don't really have a quick answer for you there, but certainly I only mention that because it's something I've been involved with. But yeah, there are a lot of other techniques. I mean, it is a multi-party computation problem, right? So there's some things. One of my colleagues at Princeton, Pratik Mittal, I don't know if you know him, but he's worked a lot on this using the ideas from multi-party computation. So yeah, it's not. I didn't mean to give the impression it's the only method. It's just the only one that I'm familiar with.
Yeah, sure. Thanks.
Sure. Thank you.
Maybe another quick question. So in federal learning, we use the server to aggregate the local information from the end users, right? And then is it, for example, if we design a very perfect privacy preserving protocol to have the aggregation of these linear parameters from the local users, and then we aggregate this final output to the server, to the centralized server, for further updating. So in this sense, is the privacy concern fully addressed? if we make sure that the local parameter aggregation is secure and privacy preserving?
Well, that's a good question. I didn't spend much time talking about this, but there is they call it the curious aggregator problem, where you want to preserve privacy from the aggregator, right? It's not just necessarily you want to preserve privacy from external eavesdroppers, right? You may not want to let the aggregator know your private information, right? So that's when you need to think about more than a technique like what you described there. So by the way, there's another technique which is called I think it's learning over the air, where in wireless you can, if you have the right information, if the right timing information, you can transmit so that in analog form, so that all the gradients, for example, add in the air as they arrive at the aggregator. So the aggregator never sees any individual gradient, okay? And that's doing something like what you're describing, except it's done in a way that the aggregator can't even see what's going on. So yeah, so if you're not worried about the aggregator, then you can do certain things. But if you don't want the aggregator to be privy to your private information, then you have to worry about other aspects of it. So I hope that answered your question. I think I addressed it.
Yeah, thanks.
Okay, thank you very much.